Hello guys, let's continue the decision analysis chapter in the second part. As you remember, the previous part we focused on a prototype example, a gopher bread company, and we just reviewed some different methods based on the situation when there is no experimentation. Okay? And we saw based on the different items what will suggest us at the result and as a decision uh, among different alternatives, and based on the bias decision rule sensitivity analysis we just learned how sensitive the results are, and we just learned a concept of crossover points. So in this chapter, we want to start a concept of decision making with experimentation. As you remember, experimentation or tests is a manner to reduce the effect, the influence of uncertainty on the decision as much as possible. Okay, and we used to improve the preliminary probabilities that we had. As you remember, those probabilities that we had before, for example, 0.25 and 0.75. Okay, so this testing can be done to improve the preliminary estimates of the probabilities of the respective state of nature provided by the prior probabilities. So as you see here, these improved estimates or these improved probabilities after experimentations, we name them posterior probabilities. Okay, so let's continue with the prototype example that we had. This time we want to enter the concept of experimentation in it, and we want to see how we should make a decision and what are the influences on it. So to this end, as we mentioned before, there is a possibility of a seismic survey, okay, a geological survey to uh, improve the quality of the decision that we make, okay, and to obtain a better estimate of the probabilities. But for sure, this one is not costless. The cost of this survey is $30,000, and we want to understand if it worth to do this seismic survey before making a decision or no. Economically, we want to check that this one if it works or not. Just to let you know, a seismic survey obtains seismic sounding that indicate whether the geological structure is favorable to the presence of oil. Okay, so let's go to the next slide. Okay, after doing the survey, the seismic survey, there are two possible results that we name them EUSS, that indicates unfavorable seismic sounding. That means that there is the probability of having oil in the land is very few, indicates oil is unlikely. The other side of the decision is FSS, favorable seismic soundings, that indicates oil is likely. Okay, and based on past experience with seismic sounding, If there is oil, then the probability of unfavorable seismic sounding is 0.4 for sure. In the case of favorable is 1 minus 0.4, that is 0.6. With the same justification, if there is no oil, it means there is dry, then the probability of unfavorable seismic sounding is 0.8. Again, with the same justification, the probability of favorable seismic sounding will be equal to 0.2, 1 minus 0.8. As you remember, in the last slides, I just focused on the concept of prior probabilities and posterior probabilities. Okay, so based on this change that is a seismic survey, we want to know how the probabilities change that finally help us to calculate the expected payoffs to make a comparison. Okay, as you remember, in the previous part we had bias decision rule. Here as well we want to follow the same line. So to this end, guys, when doing the seismic survey, okay, and based on the state of nature, totally we have 4 different situations. What are them? When the state of the nature is oil and the finding of the seismic survey is unfavorable seismic sounding. When the state of the nature is dry and the finding is unfavorable seismic sounding. Okay, these are the 2 states while the finding is USS. At the same form, we have state of oil when the finding is FFS, favorable seismic sounding, and finally state of dry when the finding is FFS. So as you see here, guys, I don't want to enter that much to this very big formula, because in the next slide you will see it will be very easy formula. This formula named bias theorem, because first Thomas Bayes just proposed that that each of these probabilities, each of these 4 probabilities, for example, for this example, P state I and finding J is probability of finding J while state I multiplied by probability of the state I divided by summation of k from 1 to n, finding and state k divided by p state k. Okay, as I told you, this formula you should just understand it. Okay, it's not that difficult. In the next slide we'll use it to calculate the posterior probabilities of our example, of our prototype example. To continue what we finished in the previous slide, based on the formula of Bayes' theorem, now these posterior probabilities can be calculated easily. Okay, as you see here, guys, as I told you, after doing this experimentation, this survey, this seismic survey, 4 possible items happen. Okay, 2 possible items when there is oil and 2 possible items when there is dry, and based on the results that are favorable or unfavorable. As an example, as you see here, the state of oil when the finding is unfavorable is the probability that we calculated and I gave you before, okay, 0.4 multiplied by the probability of the state. As you remember from the very first slide, the state of the oil and its probability was 0.25 divided by 0.4, again, that is for when the result is unfavorable, okay, and there is oil is 0.4 like here, and here guys 0.8, again the result is unfavorable. Okay, so pay attention. The important item is this unfavorable, okay, and here is this favorable. Okay, so necessarily here this 0.4 and 0.8 shouldn't be equal to 1 because they are coming from the different forms. Okay, because if the state is oil and the finding is unfavorable, okay, here, and if the state is dry and the finding is unfavorable. Okay, so this unfavorability is important for us. So the posterior probability of this item, state oil, while finding is USS, is 1 divided by 7. This 1 divided by 7 will be equal to 0.14. So the other posterior probability states dry and finding USS can be calculated easily. 1 minus 1 divided by 75, divided by 7, sorry. That is 6 divided by 7, that is equal to 0.86. Okay, so if finding is favorable, okay, if finding is favorable, is vice versa. The probability of having oil, okay, if there is oil, then the probability of feasible seismic sounding, okay, that I gave you before, that is 0.6 multiplied by a state of oil divided by this item, and the other one that is 0.2, okay, multiplied by 0.75. What is this 0.2? It is if the result is dry and the probability of favorable is 0.2. Okay, so this one is 0.5, 1 divided by 2. Obviously, the probability, the posterior probability of the other parts is as well 1 minus 1 divided by 2, 0.5 again. Okay, so now we have these posterior probabilities, okay, these posterior probabilities based on what we calculated. The next part, we need to check which decision should we select among these items. The probabilities that we calculated in the previous slide easily can be shown in this probability tree diagrams. Okay, as you remember, the probabilities were 1 divided by 7 that I told you it's equal to 0.14. 6 divided by 7 that I told you it was 0.86. 1 divided by 2 and 1 divided 2 that are respectively 0.5 and 0.5. Okay, so let's see the steps of these calculations easily in this example, in this probability tree diagram. The prior probabilities that we had are these two probabilities, yes, 0.25 when the state is oil, 0.75 when the state is 0.75. In the second column, when I'm saying column, I'm talking about these separations, okay? In the second column, the conditional probabilities, the condition of oil when the finding is favorable or unfavorable, the condition of dry when the result of seismic survey is favorable or unfavorable. Okay, so the conditional are 0.6 and 0.4 and 0.2 and 0.8. How? Based on what I gave you before. So this third column is the joint probabilities, okay? The multiplication of these two. As you remember, this part is the numerator of the formula of the posterior probabilities, okay? As you see here is 0.15, 0.1, 0.15, and 0.6, okay? The numerator. And finally, the posterior probabilities can be calculated by this numerator divided by summation of that, okay? Of that two probabilities that we have this summation here, okay? So these items exactly are our formulas in the previous slide, okay? Just check them and try to understand it well, because it helps us to do the decision trees. So if you remember our first table for the alternatives, based on the alternatives and the states of nature, okay, the alternatives were drill or cell, and the states of nature were oil or dry, were something like this: 700, minus 100, 90, and 90. Based on these probabilities that we calculated, okay, when there is unfavorable seismic study or seismic sounding, or very feasible, favorable, sorry, the expected payoff for each of these alternatives will form something like this. The expected payoff of drill when the finding is unfavorable, okay, is minus 15.7. Okay, so the expected payoff of cell for finding unfavorable, okay, guys, based on what happens, we need to make a decision, or the result is unfavorable or favorable, and based on the posterior probabilities, we need to decide between two alternatives, cell or drill. As you see here, guys, for sure the expected payoff of cell is better than drill, okay? 60 is better than minus 15.7, okay? So the other part, expected payoff if finding is favorable, okay? The expected payoff of drill, okay, is 270 based on the posterior probabilities, while this payoff, this expected payoff for cell is only $60,000. Again, a comparison between these two items. In this part, it says that In case of having favorable results, the logical solution and the logical option is doing a drill to find the oil. Okay, so this is the calculation. But in the next slide, we'll see where is the role of experimentation. Then, as you remember, in the last slides, I told you the cost of this experimentation is $30,000. Where can I see it? Okay, based on the previous slide, we just found the results if the finding from seismic survey is unfavorable or favorable, will change from sell the land and drill for oil. And the results that it gives us are 60 and 270. Okay, that the cost of survey are inside them. Okay, including, how can I understand that? You remember those probabilities 0.4, 0.6, 0.2, 0.8 that I entered. Okay, I have this cost inside it. Obviously, because the cost is $30,000, okay, it is saying that without this cost, our result would be 90 and 300. Okay, so as you see here, 90, 60, 300, 270. Okay, but as you see here, obviously excluding this cost, the expected payoff is bigger. But our question is it important? Is it necessary to do that one to do the experimentation? Why we did experimentation? To have a better results, okay? A better estimation, okay? For this reason, we want to make some tests to see if it's necessary to do that or not, or without that, and it means that without that experimentation we have the same results, okay, or not. So we need to determine potential value of the information that in the next slides we'll talk about them more comprehensively. To answer to the question of the previous slide, here we learn two methods, okay, to evaluate the experimentation and to understand if this experimentation is necessary to do or not, okay? The first method, that is expected value of perfect information, assumes that the experiment will remove all uncertainty about what the true state of nature is, and then this method makes a very quick calculation of what the resulting improvement in the expected payoff would be. Okay, as I told you, this amount that we'll learn the formulas in the next slide has a name, expected value of perfect information, that provides an upper bound. Okay, guys, it's a limitation, okay, on the potential value of the experiment. It says that up to that level the experiment can be worth, okay? If it's more than that or if it's less than that, we see what happens. If this upper bound is less than the cost of the experiment definitely should be forgone, should be forgotten, okay? Because if we want to pay something more than the permitted amount, is not justifiable. If this upper bound exceeds the cost of the experiment, means the upper bound is more than the cost of the experiment, then the second method should be used that we learned in the next slides, okay? It means that we need to calculate the actual improvement in the expected payoff and compare that improvement with experiment cost, okay? We will talk about formulas of each of these parts in the next slides. So, when we are talking about the perfect information, naturally, in each of these states of nature, we select the natural, okay, the state of nature, the action with the maximum payoff for that state, okay? As you see here, in the state of oil, it's this 700, okay? And the state of dry is this 990, because 90 is more than minus 100 and 700 is more than 90. We do not know in advance which state of nature will be identified. So a calculation of the expected payoff with perfect information, we have it here, requires weighting the maximum payoff for each, okay? 790, as you see here, for each state of nature by the prior probabilities. The prior probabilities, these 0.25 and 0.75 that we had from the prior probabilities. Okay, so the expected payoff with perfect information is multiplication of 0.25 multiplied by 700 plus 0.75 multiplied by 90 is equal to 242.5. Okay, so guys, as you remember, in the very first calculation of us, based on bias decision rule, we just found the expected payoff 100 is the expected payoff that we are going to calculate. You remember the comparison between two expected payoffs, 190 that we had, and as bias rule says, we want to calculate 100 as we want to obtain 100 as a better profit and as a better result for us. Here, as you see here, we have the same concept, expected payoff, but this part with perfect information. We just only enter the maximum payoff of each of these states. For this reason, we don't have this 90 in oil and minus 100 in dry. Okay, so here we have this 242.5, and from the other side we have that 100. In the next slide, we'll see what happens. In this slide, as you see here, the formula for expected value of perfect information is the difference of expected payoff with perfect information and expected payoff without experimentation. As you remember in the previous slide, we calculated this expected value of perfect information, okay, equal expected payoff with perfect information that we calculated was 242.5, okay, 242.5 minus, let me correct this one, 242 points here. 5 minus 100, okay, what we calculated before in the bias decision rule, okay. If you forget about it, just let's go and check it. So this EVPI is 142.5. Okay, so this is the result of EVPI. Now we need to compare EVPI with the cost of the experimentation. As you remember, the cost of experimentation is $30,000, while this cost, I will show this one with this, while this one is $142,500 is bigger, it exceeds 30. So the result, now the cost of experimentation passed the first step, but still we can't say it is necessary and it's economic to use the experimentation. The next part, that is expected value of experimentation, shows us if we should do this one or not. But at this moment, based on this result, okay, because the upper bound is greater than cost of experimentation, we follow and we do the next step to make a final decision that should we do the experimentation or not. This second and last slide of this part is the second step to calculate and analyze that if doing the experimentation is necessary or not. The name of this part is expected value of experimentation. In an abbreviated form is EVE. In the next slide, I will do all the calculations, but just here to know that this is the difference between the expected payoff with experimentation and the expected payoff without experimentation. In our example, it's 153 without the expected payoff with experimentation, and like the previous part, expected payoff without experimentation is 100. So the difference of these two elements is 53. Again, this one exceeds 30. Okay, so since this exceeds the experiment cost and the experiment cost is less than this EVE, we should do the experimentations. Now, in the next slide, let's see how we obtain this 153. To continue what we learned in the previous slide, now is the time of calculation EVE. As you saw before, we just have this result 53, but we want to know what this 53 comes. So the formula of EVE, expected value of experimentation, is expected payoff with experimentation minus expected payoff without experimentation. Expected payoff without experimentation, like the previous method, we know that it comes from the very first slides, that was equal to 100. Okay, and the expected payoff with experimentation, as you see here, guys, the formula is something like this: the summation of the findings multiplied by the expected payoff of those findings. Okay, as you remember, and if you want to see, we have these elements 0.7 and 0.3 in the slide 6 of this video, okay, because we have some extra slides here. So the numbers here with the presentation that we have in EUSS may change. Okay, so slide 6 of this video. And again, the third column of slide 8 of this video, you see these items 90 and 300. As you remember, there we calculated 60 and 270 and 90 and 300. Okay, the difference was this $30,000, the cost of experimentation. Okay, so these items should be multiplied to each other to give us the expected payoff with experimentation. So 0.7 multiplied by 90, the unfavorable, and 0.3 multiplied by 300, the favorable. Okay, that this total gives us 153. Now, the formula of EVE can be calculated easily. 153 as expected payoff with experimentation that we calculated now, and 100 as the expected payoff without experimentation. The difference of these two elements is 53. Now we should make a comparison this element with the cost of experimentation. What is the cost of experimentation? $3,000. As you see here, 53 is bigger than $30,000. So we should do the experimentation because it doesn't exceed the cost of EVE, and we need to do that. We should do experimentation. Perfect. So, in the last part of this chapter, we want to talk about decision trees that provide a useful way of visually displaying the problem and can be as well organized in a computational work, and they are especially helpful when they are a sequence of decisions, okay, to be made. Based on the sequences of decisions, we made the best decision and the optimal solution. To construct the decision tree, for example, in our prototype example, it involves a sequence of two decisions. First, should a seismic survey be conducted before an action is chosen? The second, which action should be chosen? Okay, this is our important question. Which action, drill or sell the land? In the concept of decision tree, there are some elements, okay, that show different items. For example, the junction points in the decision tree are referred to as nodes or forks, and the lines that connect these nodes are branches, okay, the lines in the decision tree. There are some nodes in our decision tree, guys, that we need to make a decision in them. We name them as decision node and we indicate them by a square. And an event node represented by a circle indicates that a random event occurs at that point. So I repeat, event node indicates random event occurring at that point. So two other items that are indicate chosen alternative. If we insert a double dash as a barrier through each rejected branch, means that branch is out of our decisions. And for sure, always to find the best decision and the best alternative, the solution is from right to to left, it means that it is backward. We need to form the decision tree and going backward to find the optimal solution. In this slide, we have all the explanations of the last two slides. As you see here, guys, the study starts with a decision node. Decision node is doing decision between doing a seismic survey or not doing a seismic survey. So we have one decision and the other decision. Let's review first this one. If we don't do this seismic survey, it means that we don't have any experimentation. It's exactly our very first table that we had in this presentation. Okay, so if we don't do this one, we need to make a decision which alternative, drilling, okay, or selling the land. If we sell the land, it gives us a value, an amount that we saw before. If we decide to drill the land for oil, two random, this node H, two random events will happen, or oil or dry, based on different probabilities that we have. So the difference between node H and node E is that node H is a random is a random event, while E is a decision node. Okay, so let's follow this part. If we decide a seismic survey, as we saw before, two random happenings will occur. A result of the seismic sounding is unfavorable. This is our EUSS that we saw before, or a favorable result, FSS. In both of these forms, in both of these unfavorable and favorable, if this one happens, again, based on the results, we have this solution and we have this option to make a decision. As you see here, node C and D. What are these decisions? Drill and sell. Drill and sell. So if we decide to drill, or here, after that, what happens? Two random results, oil or dry, oil or dry. In the next slides, we complete more this decision tree with the elements and the values that we obtained before to solve and find the optimal decision. So guys, here we enter the additional elements, okay? Besides, on the above of the branch, if there is a probability, when the probability happens after a random event, okay? And the costs of each of them below of the line, okay? So as you see here, guys, if we do a seismic survey, as you remember, the cost of this survey was $30,000. So minus 30, we should pay $30,000. While not doing that causes $0 because we don't pay anything. So in this decision node, okay, let's follow this line and continue the other lines. As you remember, we have two alternatives, two decisions, drill or sell. Okay? If we do drilling, as you remember, the cost of this drilling is $100,000. So we pay $100,000. But while we sell the land, we gain $90,000. Let's focus on the other part. What is the other part? The other part is after doing seismic survey, okay? After doing seismic survey, as you remember, the probability of having unfavorable the result, just review the other probability tree diagram that we had before, that is 0.7, while the other one is 0.3, these probabilities. Okay, so in case of unfavorable, again we have the same values, okay, the same amounts. What are them? In case of drilling, we should pay minus 100. In case of sell, we gain 90. Here as well, and here as well that we reviewed. But after doing this drilling in different cases, what we obtain if the result is oil is $800,000. But obviously, if it's dry, we don't gain anything. 800, 0. 800, 0. But as you remember, guys, the posterior probabilities that we calculated are forming something like this. Do you remember? 0.14, 0.86, 0.5, 0.5, and these are the prior probabilities. Why prior probabilities? Because they are coming from this line that we don't have seismic survey. Okay? So, what is this column here? This column is the expected payoff of each of these lines. How can I calculate it? Is the combination of the all costs. Minus 3 minus 103 plus 800 minus 130 is 670. Now this line, minus 30 plus 0 minus 30 minus 130 plus 0, so minus 130. Let's check this line. Minus 30 plus 90 is 60. This line, minus 30, 0, minus 130 plus 800, 670, minus 130, like the other one. Let's enter to this one. 0 minus 100 plus 800 is 700. This line is minus 100, while this line with 90 is always 90. Okay, so this column that we have is forming from this total of all gainings or losings. In the next slide, by entering in the probabilities, we solve and find the best solution. So finally, this slide shows these relationships, okay? These relationships and the expected payoff of each of these nodes. As you remember, always the movement is backward, starting from right hand side to the left hand side. So when we have this rightest column, 670 minus 130 and the rest, we need to calculate for each of these columns, for example, for the nodes F, G, H, and then make a decision for C, D, E, and then for B, and up to A, okay? In the A, we'll have our final decision for which element should we calculate. So just remember, I will explain it in the next slide with the formulas, but here I will explain to you. For example, for calculating the expected payoff of this node F, I need to make and calculate the expected payoff, for example, for node F from the lines that come inside to it. What are these lines? Is 670, okay, multiplied by 0.14 plus minus 130 multiplied by 0.85. If you calculate this one, this is 130, okay? If you calculate this one, it gives you minus 15.17, okay? So, as you see, guys, the other line is 60, okay? So, it's a comparison between 60 and minus 15.7. Which one is better? This one. So we need to delete this one. As you see here, guys, this line, this option, okay, this option is deleted because 60 is better than minus 15.7. The other one, for example, for this node G as well is 670 multiplied by 0.5 and minus 130 multiplied by 0.5. Again, guys, here it's a comparison between 270 and 60. Which one is better? 270 and 60. Which one is better? Obviously 270. So we forget about this line. The same here between 100 and 90, which one is better? 100, okay? So again, for this point is 60 multiplied by 0.7, 270 multiplied by 0.30. The amount that is better is 123. So in comparison between 123 and 100, the better result will be 123. So as you see, we delete this line as well. Okay? So what is the optimal decision is doing a seismic, okay, is doing a seismic survey, okay. If the result is unfavorable, sell the land, and if the result is favorable, drill for oil. In the next slide, I will write all the calculations for node F, G, and H, and for the rest, you can write it you yourself. To clarify the items that we had in the previous slide, in this slide, as you see, I just put the calculation of the expected payoff for the nodes that are random nodes, okay, that are event nodes. That are F, G, H, and B. As you see here, guys, They are the combination of the probabilities multiplied by expected payoff that they are coming from. Okay, these items helps us to make a comparison, okay, and delete the items that are worse than the other one up to finding the best solution. I repeat, what is the solution? The solution is doing a seismic survey as we reviewed before, okay? And if the result is unfavorable, the alternative that we select is selling the land, and if the result is favorable, we select the alternative of drilling.